Frederica. Thank you for inviting me. Thank you for organizing this. Hello, everyone. So, as Frederica said, I'm going to try and give you an overview of work I've done over the past few years on tidal mixing. So it's both old and new work. I hope it's not boring for some of you who might have seen this already or part of this already. But there will be some recent results as well. So let me start. Here is a quick outline. So I'll first describe tidal mixing parameterization that I've worked on. Then I'll describe the 1 degree global configuration of NEMO, which we set up in recent years. And finally, I'll show you some impacts of different tidal mixing schemes in this global ocean configuration. So let's go first to the tidal mixing parameterization. I'll try to give some details so that we can relate this to EDMX. It's very much similar to EDMX, and it was essentially inspired by EDMX. So what is tidal mixing? When you have a tidal flow, an oscillating tidal flow interacting with a topographic slope, what this tidal flow does is it displaces these isopycnal surfaces that are shown in black on the top right here. And by displacing periodically these isopycnal surfaces, it creates waves, which we call internal tides. And these internal tides, they can be of small scale. Usually we then call them high modes. And if they are of small scale, they are more susceptible to instability, and they will tend to break close to where they are generated here along the topography. And so they will generate local mixing. Now, there are also large scale internal tides that are generated, which we call low modes, and which will feed the internal wave field of the global ocean, and they can propagate for thousands of kilometers, and they will ultimately fuel mixing in areas remote from the generation site. So to illustrate these two types of mixing, I have this famous transect of turbulent diffusivity from Paulzin et al. 1997. So this is a transect going out from the Brazil coast towards the mid-Atlantic ridge on the right. And you're looking at diffusivity in centimeters squared per second. It's based on microstructure data. And essentially what this figure showed is that above the rough topography of the mid-Atlantic ridge, you have elevated diffusivities. And elsewhere, either in the upper ocean or in the western part here of the basin, you have fairly weak and uniform diffusivities. So it's been shown that these high diffusivities close to the rough topography, they are essentially due to local tidal mixing, so high modes internal tides. And whereas the sort of mixing that's elsewhere, that's much more uniform, it's actually largely due to low mode internal tides that can come from elsewhere, as I will try to show soon. So we want to improve the representation of these two things, and there's been a way of doing the sort of local bottom intensified mixing for a long time, and usually you combine this with a background diffusivity. That's the sort of old way of doing tidal mixing. And what EDMX and my work have tried to do is to have a sort of more explicit representation of this low mode remote mixing pathway and have something that's energetically consistent. So here is the methodology that we developed. So we want to track the energy of internal tides from sources to sinks. So we start from the generation, which has been decomposed into vertical normal modes by Falahat et al. We also have an estimate of internal tide generation by abyssal hills from Mellet et al. So we start from these static maps internal tide generation, and then using the climatological stratification, we track the energy beams in a Lagrangian way, and we try to estimate the dissipation of these low modes. So here I start with modes 1, 5, which we've found propagate significantly. So we track where they go using linear wave theory, and then we try to estimate the dissipation due to 4 processes: interaction with critical slopes, critical topographic slopes, shoaling, so that's when an internal tide goes into shallower water and its energy is concentrated in a small water column, so it tends to create direct breaking of the tide. Then we have another process which we estimate in a simple way, that's dissipation by wave-wave interactions. And finally, scattering by abyssal hills. So abyssal hills are really the small-scale roughness of the seafloor. Now, this 2D mapping here from the generation to the dissipation, we do it with an observed WOS climatology of stratification. So all this is, we get essentially 4 static 2D maps of dissipation. What I should have said is we find that modes greater than 6, they don't propagate much at least at the resolution of our calculation, so half a degree. So they move directly to these dissipation maps. So once we've done this 2D mapping, which is just a climatology, we're going to use these 2D dissipation maps to get a 3D distribution of turbulence production. And to go from 2D to 3D, we need vertical structures, and we'll apply a specific vertical structure to each dissipative process, because we know that a different dissipative process will lead to a different structure of dissipation. Now, this vertical structure of dissipation, they often depend on N, so the buoyancy frequency. And this is now going to be interactive when you use this parameterization in a GCM. So the vertical structure is applied to the model simulated N squared. So I won't say much more here, but essentially we end up with so these 4 contributions to turbulence production, which we sum in the model, and we finally deduce the diffusivity from this turbulence production. So now, as I said, this work was really inspired by EDMX. So here I tried to give you a very quick comparison of the differences with the EDMX approach. So on the same diagram, essentially I tried to show what Eden and Olbers proposed in 2014. So here it's only the generation which is static. So you have static 2D maps of generation, which you still have to read. And then the rest is done online. So the generation was split between mode 1, which was considered to be the sort of propagative part, and modes greater than 1 assumed to dissipate essentially locally. And then the propagation is done with the Aurelian scheme of the model, and much like we do, there is an estimate of dissipation by continental margins, wave-wave interactions, scattering by abyssal hills. And finally, there is a scheme to distribute the turbulence production in the vertical with up and down propagation and a dissipation formula based on weak wave-wave interaction theory. So the key difference is basically I take these 2D dissipation maps to be static, whereas EDMX only takes the generation 2D maps to be static. And the sort of rationale for the simplification I made of not doing this part here online is the idea that this propagation part is potentially computationally costly in a GCM, and also I was guessing that this would not be very sensitive to changes in stratification overall, and I sort of tested that assumption. So I made this simplifying choice to sort of save time and also simplify the whole procedure. So the parameterization I propose is just based on 4 static maps of dissipation. So that's the internal tide energy dissipation integrated over the whole water column. Due to 4 processes. So I show these 4 maps here. There is wave-wave interactions. That's the main part of the energy. So that's very much distributed across the global ocean. So it's shown on a log scale from 10 to the minus 6 to 10 to the minus 1 watts per meter squared. This is the map for shoaling. So you see that this is really mostly at the shelf break and really near the continental margins that the shoaling of internal tides is a key dissipative process. This is the estimated dissipation due to interactions with critical slopes. So that's mostly occurring at steep continental slopes. And finally, this hill component is the dissipation due to scattering by abyssal hills, as well as generation by abyssal hills. And that's mostly strong where you have these slow spreading ridges, which are quite rough and quite rife with abyssal hills. So that's how they look like. And then what we need to apply the parameterization in a model or on a climatology of stratification is a vertical structure. So we use simple structures based on previous literature. So wave-wave interactions, it was shown that this leads to dissipation largely proportional to n squared in the vertical. The turbulence production in the vertical is set as proportional to n squared for this part, as proportional to n for this part, which is because this is mostly direct breaking of the internal tide, leading to a slightly different structure. For the critical slopes, we simply use an exponential decay above the bottom because that's supposed to cause mixing really along the topographic slope. And finally, for the hill component, it's only slightly more complicated. There is a fraction that's sort of decaying with height above bottom. So HAB here is height above bottom. So that's decaying algebraically with height of bottom. And there's another fraction which is simply proportional to n squared. And so this comes from Paul's in 2004 and was shown to work very well in the Brazil Basin. So there are 3 parameters here that have been chosen based on the topography, the observed topography, and also tuned to match the microstructure observations. So they are not parameters in the GCM; they're really set once for all. So that's the idea. I'm going to show you. Yes.
Can I ask the question?
Sure, go ahead.
In this 4th mechanism, the n dependence or n square dependency, isn't that double counting with the first one?
What do you mean is the first one?
I understand that part of it is this bottom, and the other part of the Paul's-in 2004 mechanism is the normal wave breaking, right? Proportional to n square. But that you already have in the first box in the upper
yes left. Yes, that's right. So this choice was really designed to match the observations in the Brazil Basin. So so the idea is that there's above abyssal hills, there's going to be very high modes that dissipates really mostly close to the bottom. So this is really very strongly bottom intensified, this formula here. But there is also some sort of somewhat higher modes that are able to propagate up and down, and that will ultimately cause a dissipation that's actually mostly in the Picnock line, so proportional to n squared. So it's still this is still coming from internal waves that are being generated above abyssal hills. At least that's how it's calculated. So it's slightly different from this, at least in the calculation. Now, of course, in the GCM, to make things simpler, I added this component to this map so that the code is as simple as possible. So it's not really double counting. It's just that the abyssal hill part, I found that it works better if some fraction is actually distributed as n squared rather than only set at the bottom. And admittedly, it's fairly ad hoc to have just one fixed parameter for this, but it works. It works really well. I don't have the detailed figures on this, but I'll show you soon that it works fairly well in terms of reproducing microstructure observations. And it also fits with what Paulin was saying in his paper. You also need some dissipation higher up to match the observations.
I have another question. You have your energy input, right? And then you have your energy fields from that. And then you end up with these dissipation rates or these work densities or whatever. So how does it work? How can you come from the energy to the energy dissipation?
Oh, I see. So I never really have I don't really have the energy. I propagate energy fluxes really. So it's really the energy fluxes that are this is a power, of course, the generation rate, and then I propagate the energy fluxes and I dissipate these fluxes into D. So I don't have to convert like in EDMX an energy content into a dissipation rate. Because I only have fluxes, and I can deduce the energy content from the calculation, but it's not. It's only a diagnostic. It's not really part of the scheme.
And the power distribution into these different processes, how is this controlled, and how much it goes to wave-wave interaction, and how much to the others?
So it's controlled by the by my parameterizations or my representation of these dissipative processes. So here I have a formula by Buller and Holmes-Serfon for this one, which is quite similar to what you had in EDMX, but a bit smaller, a bit weaker, factor of 3 to 10 weaker. For critical slopes, I have also estimated this for each grid cell in the global ocean, the sort of fraction of energy of a beam that will intersect at least with a critical slope. So each of these processes has sort of a parameterization, and then the calculation ultimately will give me what are the fractions, right? What is the power? And so this one is the simplest in the sense that it's just a decay time that depends on latitude for this one. So it's an emergent, this power that I show here is really an emergent property of the calculation. It's not fixed from the start. It's really as you propagate the beams, they dissipate due to this and this process, and you're left with that much energy, and you go to the next grid cell, etc. And you end up with this distribution, which seems to reproduce really well the observations, as I will show next.
Okay, and will you say more about the Lagrangian energy tracker?
Yes. So yeah, I should have taken more illustrations of this. I have one figure at the very end if you want more info on this. So yeah, I track the beams. So in a Lagrangian way. So from one grid cell to the next, when the beam arrives in the grid cell, I will calculate analytically where it's going to end up, accounting for refraction. And I will decrease its magnitude, accounting for the four dissipative processes. So it's really a very simple code that I made myself, and it's quite fast. I mean, it takes an hour and a half on my laptop to compute the whole mode 1 distribution, for example. So I track the beam one by one. Yeah, really, each beam is tracked one by one, and whenever I encounter a supercritical slope, which means reflection back to the open ocean, I save the energy on the supercritical slopes, and I will reuse this energy as a source later on. So it's an iterative process to track all of the energy. Yeah, I can.
But the Lagrangian or this ray tracing gives you the trajectories, right? But if the trajectories diverge, then there is this thinning effect of energy, right? This kinematic thinning, if you want. How do you deal with this?
Yes, so this is not going to be dealt with really. So each trajectory is assumed to be assumed to have infinitesimal widths, I guess. So the only way we may maybe implicitly account for this is that we split each source is sort of distributed in angle, and so each angle bin, which is we take a small angle bin. I don't have the exact number, but a few degrees for each angle bin. We'll have one trajectory. So it works. It works really well this way, but there's never going to be an explicit way of having a thinning or thickening of a beam, because a beam is going to be represented by several infinitesimally thin rays, basically.
You say that the energy E dot along the slope, along the ray, is conserved.
Yes.
Which is not.
Yes, I think that's correct, except for dissipation, of course. So I think that's correct. Yeah. So I don't think. We can discuss this at the end. I have one figure showing a bit more maybe some beams going around. But I don't think I will have explicitly thinning or thickening of the beams. And I don't think it's a big issue for getting the sort of realistic to the dissipation maps here, but it's a good question.
Casimir,
yes.
Can I also ask a question? So
sure.
Your Lagrangian tracker, is it like a bit like once you get the direction from a beam in the beginning, then it's instantaneous? It's like this beam is going to once it hits a slope, and which is once it's a critical slope, then it's reflected, and so it's like an instantaneous way of this beam, and then the flux is taken out according to your formulas, and then how much ends at a certain location depends on how much was taken out on the way of the beam, basically. Do I understand this correctly?
Yes, that's right. So each beam is tracked independently. So the beams don't interact with each other. And it's done once for all on the climatological stratification. So I take a beam and I propagate it from grid cell to grid cell until there is no more energy flux left in that beam, essentially. And then I move to the next beam. So, and in the end, I have an annual mean map of dissipation. So there is no problematic of synchronicity, or because each beam is independent and it's done on a climatology. So time, there is no time, basically. Time doesn't matter in my calculation because it's just going from one grid cell to the next and dissipating.
How do you know the original directions? I guess there are plenty of options, and Frédéric is also working on that. But what are you using?
Yes, it'd be great to have really properly calculated directions, as Frédéric has done. So for now, what I did is I used the large-scale topographic slope as a proxy for the direction in which the beam goes. So I send the beams away from the topographic slope, basically, to avoid, sending the energy directly upslope, which is not really realistic. And so and I found it gives me the right direction of the very well-known beams, like the one going from the Macquarie Ridge to Tasmania, or the large-scale slope seems to be a reasonable proxy for these big beams, but it's pretty ad hoc, and it's a best guess. In many ways, in many instances in this calculation, I had to do really rough. You have to do a lot of rough choices, and a lot of you have to do a lot of assumptions. But the fact that I can compare well to observations at the end makes me think that it's justified to do these rough assumptions. So if I move on, but feel free to stop me. So I have a few slides on comparison to observations. I'll try to go a bit faster. So this is microstructure data that we compiled. So we have 19 projects, 11 almost 1,200 profiles. So obviously the sampling is sparse. It's better in the Atlantic than elsewhere. But this is what we have, and I think it's enough to get some constraints on what we're doing. And so what we can do here is or what I did, I guess, is to plot a project average profile from each of these projects that you see here, and I compare with my parameterization, so my sort of 3D map of dissipation based on the WOS climatology here. So I compare what the parameterization predicts at the exact same locations. And so I get these kinds of profiles for all each project. So you have in black you have the observations, and in blue you have the parameterization. And obviously, I won't go in details for each of these projects. Just see that you have a scale goes from 10 to the minus 11 to 10 to the minus 6. So you have 5 orders of magnitude here. And in general, the parameterization sort of captures the sort of broad shape and the broad magnitude of dissipation in these locations, with of course some exceptions. So we have too much here near Japan and the Izu Ridge, and in the Southern Ocean, these 3 projects here in the Southern Ocean, the agreement is also much less good than elsewhere, I found, and this is consistent with the notion that mixing in the Southern Ocean is not as much due to tides as it is elsewhere. And this is another set of projects going a little bit shallower. So I guess what I was happy with the fact that, in the Indonesian seas here, I could retrieve very high dissipation rates, whereas in the North Atlantic subtropical gyre, I have these fairly weak dissipation rates. So we seem to get the sort of big spatial contrasts in dissipation. Perhaps more visual is this transect. So this is the exact same transect I showed in the introduction from the Brussels Basin. Essentially, but now we're looking at dissipation on a log scale in watts per kilogram instead of diffusivity. So the data is at the bottom, and the parameterization is at the top. And essentially, what you can see is that we can sort of reproduce the contrast between the deep and the upper ocean, and also the contrast between the eastern part of the basin and the western parts. And sometimes we get agreement, down to the details, which is fairly encouraging. More quantitatively is this. This is a scatter plot of the dissipation from microstructure data. So the whole, all these projects, all these profiles in 3D compared to the parameterization or the sort of 3D map I produced. So if I take all these measurements and all the ones we have, we see that basically we seem to have a good correlation and pretty good order of magnitude agreement. So 85% of values agree within an order of magnitude. And the correlation if you use the log scale dissipation is significant, 0.57. If you use the raw absolute values, it's not significant. Now, I also did, like Federico did for EDMX, I did some comparisons with Argo fine structure dissipation. So this is a sort of more indirect way of measuring dissipation, but it's supposed to be dissipation due to internal waves. So in that sense, it's a good comparison to the parameterization. So this is a map at 400-meter depth from my climatology or my parameterization, and this was Caitlin Whalen's estimates at 400-meter depths. And again, basically what I was quickly encouraged by the fact that you seem to recover, most of the sort of big geographical gradients in dissipation, and sometimes down to the details. Although this seems to be a bit more uniform than the parameterization, which has slightly stronger hotspots and also slightly weaker mixing in some parts. So again, that's the visual comparison. The more quantitative one is this. So these are scatter plots comparing the dissipation in this study, again in 3D compared to the fine structure. And on the left, it's the Kunze ship-based fine structure estimates of mixing. And this is the Whalen Argo-based mixing estimates. And again, the sort of correlation is pretty obvious over several orders of magnitude, with around 90% of values agreeing within an order of magnitude in each of these two data sets. Well, so I found this quite interesting, not just, to say this parameterization is good, but more to say actually tides are really the main factor generating spatial contrast in dissipation and really the main agent of mixing in the ocean interior. To me, that seems quite clear from these comparisons. So now let me move to more recent work, and I'll be brief. So what I did more recently is to put this mixing scheme in NEMO and then try and evaluate its impact on the ocean state, comparing with an older classical scheme of tidal mixing. So quick overview of the configuration. It's global, 1 degree in the horizontal, 75 layers in the vertical. I used NEMO 4.2, so the sort of latest stable release. The forcing is a normal year forcing, core version 2. I have geothermal heating also at the bottom. And I run these simulations for 1,000 years, up to 1,500 for one of them. And so I mostly focused the analysis on the last decade, because there is very little drift and variability at the end. Now, the main, I guess I should say directly that basically we find weak sensitivity to the tidal mixing scheme. But I'll explain why, but definitely the sensitivity is weak, but perhaps the value of this study is more in the fact that we managed to get a fairly realistic or a reasonably good ocean state. So we did a lot of calibration and evaluation, focusing on the freshwater balance, the drift and biases in hydrography, the mixed layer depth, sea ice extent, and mostly trying to have a good southern ocean, because this is where we had huge biases to start with. So after 1,000 years, the circulation reaches a quasi-steady state. The ACC is 172 spherodrops, so just at the high end of recent observations. The AMOC is 17. The abyssal cell is about 10 spherodrops. Slightly weak, but not very far from inverse estimates. The AMOC is a bit shallow. It's biased shallow. Yes.
Sorry, Casimir. Is this calibration for the model with the new scheme or without the new scheme?
So yeah, that's something I should say from the start. So the calibration is not, it was does not involve the tidal mixing, because essentially I get the same ocean state for different tidal mixing schemes. So it's mostly other parameters that I've worked on, but it's true that I use the latest scheme to do the calibration. But it turns out that the sort of ocean state is not very sensitive to the tidal mixing scheme. So I could have done the calibration based on the sort of old mixing scheme. It would have be fairly similar.
Okay.
But it's true that this is a classical bias of papers, is you tune your model based on your most recent parameterization. So that's a classical classical bias, I guess, that we have. So in terms of MOC structure, there's a shallow bias of the AMOC, which is quite classical, but the abyssal MOC is really compressed towards the bottom, as you would expect from theory. A quick illustration of what we achieved with calibration. So mostly we looked at mixing parameters other than tidal mixing, and we also looked at some sea ice parameters, etc. And we tried to fix the Southern Ocean, because to start with, this is a transect of the Atlantic before calibration, showing temperature at 30 west. And so we had this very cold Southern Ocean, very cold abyss compared to the observations. So here you have an observational climatology at the bottom. And essentially what we did is we sort of tuned away the strong open ocean convection that was depleting this subsurface heat reservoir. And now we have a fairly realistic subsurface heat and generally fairly good Southern Ocean hydrography, and also a much better abyss. I mean, much less cold and dense. So that's the main achievement really of the calibration.
Casimir, how did you do this? What did you change to go from one to the other?
So I change a lot of things. So mostly isopycnal mixing. So both tracer mixing and Ghent-McWilliams. I changed these two things. I changed the surface boundary layer mixing. I changed the air ice drag of the sea ice. And I changed the way the freshwater budget is closed, but I think that was a sort of minor effect. So that's it. Really, so it's essentially surface boundary layer mixing, lateral mixing, and sea ice. A few parameters in the sea ice actually, but the most important one was the air ice drag. I can't say exactly what works, because this is old way of tuning. I just run for a few years. I see whether I'm diverging away from the ops or not, and I make my choices informed by my understanding of the physics and by comparison with hydrography and comparison with observation. So I did probably like 50, at least 50 simulations to calibrate. But they were only 10 years long or something like that. And only from time to time, I went to 100 years. And when I started to be happy, I did 1,000 years. But I can't tell you exactly which parameter is the most crucial. So perhaps a good surprise, but I'll go quick here. A good surprise was that we seem to get fairly realistic Antarctic bottom water formation on the shelves. This is illustrated here. You have the bottom neutral density in the observational climatology on the left and the model equivalent on the right. And essentially, you get bottom densities above 28.5. So this is typically a dense shelf water in 4 regions, which are the same 4 regions where we know we have Antarctic bottom water formation in the real world. So that was a surprise, and if you look closely, you can see that it actually does propagate downslope from these regions. So we have very little open ocean convection, and we do have 4 different sites of dense shelf water production, like in the Alps. And so I confirmed this with a sort of dye, an artificial dye release. So I release a dye at the surface, and then I see how it spreads. And so here you're looking at the concentration of this dye in the bottom grid cell of the ocean after 10 years and after 30 years. So you see that if you release a dye at the surface of the Southern Ocean, after 10 years, the only places where it has gone to the bottom is really in these regions of dense shelf water formation, essentially. And then it starts to spread downstream. It cascades down the continental slope.
This is
Yeah,
it's very nice, right? But the bottom density was still too light, right? So there is too much mixing of the downslope.
Yes, yes, exactly.
The bottom boundary layer parameterization in it or something?
Yes, so that's right. I was trying to go fast, but what you see is that you lose too much density still when you go down the continental slope. So that's the classical problem of Z coordinate models, which have too much mixing along the continental slope, so that the bottom waters are eroded too quickly. And so this still happens here. We get a too strong density loss as we get down the continental slope.
But there's no cure for that, or attempt to cure this with bottom boundary layer parameterization or something.
There is in NEMO the Campin and Goose 1999 scheme to help with the downslope flow, which is activated. It helps a little bit. But you would need more work to really get to the observations. So there is something in NEMO, but it's certainly it can be improved. This is part of the things I would like to work on.
I looked at the results of your data in the front of the Antarctic Peninsula and compared it to results from observations I analyzed, and they predicted very low orders of magnitude, like 10 to the minus 11, which were way lower than what I see in the bottom boundary layer of the gravity torrent. So like all the predicted tidal mixing is probably too low, but then you have all the artificial spurious mixing and makes it probably way higher than the observed dissipation rate. Did I understand that correctly?
Yes, I think you're right. Yeah, I think you're right. You will see that in different simulations there will be very different levels of tidal mixing around around Antarctica. I'll show next, but I think you're right that in typical runs we don't have enough tidal mixing around Antarctica, but we have we have way too much spurious mixing. So it's definitely, I think, spurious numerical mixing that causes this big density loss from here to here. Now it turns out that we have sort of the right bottom densities when you go further north inside the basins. So there is also a compensation of biases where we lose too much density here and not enough across the ACC. So modeling is a complicated it's a complicated thing, because you have a lot of different biases, and it turns out in these simulations we were fairly lucky, basically, because we seem to get sort of a realistic density stratification, but partly by chance. So I think I'm already way over time. What I perhaps can say is very quickly that we have done then two, with this configuration I described, we have done 3 different simulations called old, new, and TRR here. So one is the old scheme, so Simmons et al. 2004. New is the parameterization I just described. So these maps show the total power in each water column on a log scale. And then finally, I have a last simulation. Maybe I'll just say a few words about this, where I used the parameterization I described, but I added subinertial bottom trapped internal tides based on Muller 2013. So I used this Muller's estimate of subinertial internal tide generation, and I added this to the parameterization. And you might see here that it increases a lot the mixing in the Southern Ocean, and also in the northern high latitudes compared to the standard. So so that's and it seems to improve the simulations overall. It produces a bunch of biases, so it seems to go in the right direction. But the bottom line is that we find fairly weak sensitivity of the ocean state to these different mixing schemes, partly because the sort of bulk mixing is very similar. When you use the background diffusivity of 10 to the minus 5 plus the local bottom intensified mixing, you get fairly similar amounts of mixing average over a basin. And that means you get sort of the same kind of response. So just to follow up on Ole's comment, when you add the subinertial internal tides, you have a lot more tidal mixing around the Antarctic continent. So this is without subinertial internal tides, and this is with. So you see that the Southern Ocean map is really different. And because of this, there are interesting effects where this increased mixing around Antarctica tends to erode the CDW heat. And so it reduces the sort of heat content around Antarctica that can reach the ice shelves. So that's perhaps the most important thing we found in doing all these simulations. So I'll skip this, but I can go over this in the discussion if you want, but I'm just going to highlight this result, which is that when you add subinertial internal tides, this is the maximum temperature in the vertical in the Southern Ocean. In the observations at the top left, in the standards, well, the new experiment, so with my parameterization, and then when you add subinertial internal tide, this is TRR minus nu, you find a pretty substantial cooling here around Antarctica, which is due to these subinertial internal tides, and this reduces the heat that is able to reach Antarctica. So it's a cooling of CDW essentially. So I'll go to my conclusions now. So the take home is we have a sort of calibrated global 1 degree configuration of NEMO, which has ABW formation on the shelves, somewhat surprisingly. And we're happy to share all the ingredients of these simulations. The second point is that there's an improved parameterization tidal mixing implemented in this model, and this also includes subinertial internal tides, and it's included really in the code release, so it can be used straight away. And finally, the sort of scientific take home here is that the global ocean state is weakly sensitive to the improvement in tidal mixing, but the regional ventilation does change. We found a 10% strengthening of the AMOC, and also the fact that subinertial internal tides, they tend to shield Antarctica from CDW heat and to rejuvenate the deep ocean, so reduce the deep ocean age. Thank you.